Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome back in lecture 02 part 8. Student, this lecture is very important regarding the load transfer mechanism. I see so many students when they are analyzing a beam, and when any such type of questions came or they face such kind of problem, when they are facing a slab system and they are asked or questioned to find out the loading on the beams, so in that case the students are unable to calculate the load over the beam from the slabs. So this is very important question. In this lecture you will see how to calculate a loading on a beam, or you will see how loads are transferred from a slab system to a beam in one-way slab system and two-way slab system. Both cases are important. The first, in this part you see, or in this figure you see a one-way slab system. So I have already designed this beam as you see here, G1 and B3, B4, B3 beam. I have designed this in one of my examples which are available on my YouTube channel. But let me discuss the one-way slab system. Here you can see the span is 33 feet and 6 inch. Here it is 30 feet and here it is 33.5 feet. But the shorter side is 15 feet. So that's why if you divide 30 divided by 15, or if we divide 30.5 divided by 15, so the ratio will comes out to be more than 2. So that's why we can say this slab system, right? You can see here this one, it is a one-way slab system. So I have already calculated this one-way slab system for the design of this beam. I will share the link of that example in description. So in this case, basically the tributary area for this beam, that is G1, denoted by B3, B4 and B3. So in this case the tributary area will be look like in this shape, right? This is the tributary area for this B3, B4 and B3 beam. Now what will be the width of this area? This width will be equals to this 15 feet, or you can say this span divided by 2 and this span divided by 2. So both spans are equal. 15 divided by 2 plus 15 divided by 2, it comes out to be 15 feet. And the overall length of the beam will be 33.5 plus 30 plus 33.5. So it will give you the overall loading on this beam, right? So in the case of a one-way slab system, it is so simple to calculate the loading over a beam. As you see here, this example, that in this case you can see LX and LX this is the shorter span and LY is the longer span. So the tributary area for this beam, it will be equals to the dash lines, as you can see here. The width of this tributary area will be equals to LX, right? This LX. But remember, if this span and this span is different, so in that case this span LX divided by 2 will be considered to be this distance plus with this distance, that is Lx divided by 2. So that why in this case both both this span and this span are same, so that why the width of the tributary area is Lx. So it is simple to calculate the loading over a rectangular beam in the case of one-way slab system over the beam. Remember, let's say if we have an cantilever portion, right? Let's say we have a cantilever portion right to this side, right? So in that case the tributary area will be extended, right? This areas will also be act over the beam, but remember this is my beam. So in that case it is important to counter this area as well, right? But remember, if let's say we are designing this beam, so in that case the tributary area will be this cantilever area that will be directed transfer to this beam. This is important. This is very, very important. This total cantilever loading will be transferred to this beam like this one, and the half of this Ly, right? The half of this Ly, that width will now this one, that is Ly divided by 2, right? And this cantilever portion length. So that why the equation or the formula for a one-way slab system will be, or you can say the width supported by an exterior beam, by an exterior beam will be equals to Lx divided by 2 plus cantilever portion if any. If any. Sometime we have, but sometime we have not. So like in this case, this is my exterior beam, similar this is my exterior beam. So in that case, let me rub this one. If let's say we are designing this beam, this one, this is also an exterior beam, and we have a cantilever portion right here. So in this case the width supported by this beam, right, the width supported by this beam will be equals to, right, this one, right, this area, this area is Lx divided by 2, and this is my cantilever length. So the overall width supported by this beam will be equal to Lx divided by 2 plus cantilever length, and it will be multiplied with the length, so we will got the total area. This Lx is the shorter direction, Ly is the longer direction. A one-way slab system is easy. I have already do this example, right, this one, and it is available on my channel, so please go there and watch how to transfer the load from this slab system to this beam. Now the two-way slab system is a little bit complicated, right? Like you can see this a two-way slab system, and here you can see this is 17.75 and this is 15.75. you divide it, the ratio will be less than 2, so that why all the panels are a two-way panels. Similarly for this one, similarly for this one. So all the panels, this panel, this panel, this panel, similarly this one, this one, this one, all these are the two-way panels. Now in this case, if you want to calculate the tributary area, so here we have 4 cases, right? So here is my example. here you can see Ly. So Ly is my longer span and Lx my shorter span. And here you can see we have B2 beam, we have B4 beam. This is my B4, this is my B1, this is my B4, this is B3 beam, this is also B3 beam, and here is my B2 beam. So let's say we are considering the B1 beam. So you can see in the case of two-way slab system, the tributary area or the slab loading is distributed into both direction. While in one-way slab system, the load is only distributed to one direction. But in a two-way slab system, the load is distributed to 4 direction. It must be remember, the load is distributed in a two-way slab system. It is distributed to in this direction. It is distributed to this direction, in this direction, similarly in this direction. So the load comes to this beam as well, this beam as well, similarly this beam as well, and this beam as well. Similarly to this beam, load comes out from that beam as well, similarly to this beam from that panel as well, right? So and this beam, which is denoted here B1, right? So the load is coming from 2 direction. But in this case, in a two-way slab system, the total area is distributed into trapezoidal area and triangular area panel, and then this in this shape, right? This is my shorter span, that's by Lx. This is my longer Ly. So here is my, right, similarly to this side, right? And let me rub this. Similarly here, and over this panel, right? So this kind of mechanism you can see here. To this beam, loads coming from this trapezoid, and similarly from this trapezoid. Similarly to this beam, which is denoted here by B3, B1, loads coming from this triangular area, loads coming from this triangular area. Similarly from this trapezoid to this beam, from this trapezoid to this beam, right? Similarly here, similarly here. Similarly at the exterior beams, we can see here. So in this case, only one trapezoid area, similarly here one trapezoid area, similarly here. While on the shorter beams, you can see one triangular area, one triangular area. So this is overall mechanism, right? And I have pointed right here. And remember, this is very important point, that these trapezoids are at an angle of, this trapezoid is an angle of 45 degree. It is assumed all the angles with beam is 45 degree, all the angles. So you must understand this, right? Now let's say we are calculating the beam over this B1 beam. Noting this point here, that here you can see the loading, the area is triangular area. So that's why the load over this beam will be triangular loading. And I have already shown this here, that this one, the loading will be a triangular loading. But remember, we will convert this triangular loading to an equivalent UDL loading, uniformly distributed, because the analysis for such kind of loading is very difficult. We will convert this triangular loading to an equivalent UDL loading by multiplying this triangular loading with a factor. right? We will multiply this with a factor to counter for that, for her triangular, because the moment in this case you can see here will be different from the UDL one, right? So that's why we have to convert this triangular load to make the calculation more simple. This is important. Now the the side, this side of this triangle, because the length of this beam is Lx, so we need to find out the area of this triangle now, right? The area of this triangle can be easily calculated, or from this triangle it can be easily calculated, because the span is Lx, and the height of this triangle is Lx by 2. So it is easy to find out the area of this triangle, right? The area is nothing, it is half times Lx divided by 2 times Lx, right? So this is Lx square divided by 4. This is the area. But this is important that in this beam B1 we have two triangles, so we multiply this with 2 cancel with 2, so that why the area of two triangles will be Lx square divided by 2. So this is the area, and we will multiply this area if you want to find out the load on this beam B1, right, on B1. So it is simple to find out the load, but that load must be multiplied with a factor to counter for, because we are converting this triangular loading to a UDL. So if you want to convert this triangular area into UDL, you have to magnify the load, right? So in this case, like the shorter interior beam, the load will be, let me write down this here, this is my first case. This is my first case, load over shorter interior beam. Interior beam B1, sorry. Now the load will be the equivalent slab width for calculation of bending moment, right? The equivalent slab width, because we find out the equivalent slab width. So equivalent slab width for calculation of bending moment will be, remember, right, this 4 by 3 factored, it is the modification factor which convert the triangular load, because it magnify the triangular load and convert it into UDL. So this is the factor we have to multiply. This is the area, and if you divide area by the length, we got the width of this triangular area, equivalent width, right? And this equivalent width, 2 by 3rd of Lx, it will be multiplied with the unit calculated load, right? it will be calculated, it will be multiplied with WU, right? So we'll obtain from this, let's say, X pound per feet loading or kilonewton per meter loading, right? So this is the way, right? We will do example over this kind of calculation, but you must remember these points, that how we get this equivalent width, right? So this is the first case. We can write down the same cases like this for this B2 beam. So here you can see we have only one triangle. So in case of one triangle, right, now slab width supported by exterior smaller beam, right? Now slab width supported by this exterior smaller beam, that is B2. So in the case of B2, what will be the equivalent width? This is important. In this case, the equivalent width supported, or the equivalent slab width, it will be equal to, remember, if there is any cantilever portion, let's say if there is any cantilever portion, so that portion must be added, right? It is, in this case, it is equal to, will simply be half as that of the interior beam, right? Like you can see here, what we got here, it should be divided by 2, right? The equivalent width for this smaller exterior beam will be 2 by 3rd. We have to half it, this loading, this width. So that by 2 cancel with 2. So, and plus any cantilever portion. Right? This is important. So remember, this is for B2, the equivalent width. This is very, very important. You have to remember this equation because we will use these equations. So 1/3 Lx plus the cantilever portion. And similarly for the longer case, right, you can see here for B3 and B4. Here we can see that for B3 we have trapezoid right here, and we have 2 trapezoid here. In this case we have 2 trapezoid, while in the B4 we have 1 trapezoid. So we have to find out the area of this trapezoid, and then we have to multiply that area by the factor, right, and then divide it by the length of the beam. So we will got the equivalent slab width. This is important. So this is case 3. Now slab width supported by interior longer beam, that is B3. This is important. Now Now here you can see here, if you observe this figure, this is important, this figure is important. Let's say we consider this case, let's say, right, we consider this case. So here let me make this a little bit prominent to understand it completely. Now here you can see this B3 beam. So here we can see this is my trapezoid, right? So we see here the this triangle right here and similar triangle right here. As this triangle contributing loading to this beam, similar this triangle contributing to loading this beam, so that why this area must be subtracted. This area must be subtracted from the overall panel area, right? Overall panel area. So actual area supported, this is important. Remember, this is important. The actual area supported by this beam, this one. Let me. What should be the net area, right? Noting this one, what should be the net area of this total panel, right? This total panel. Or you can see what should be the area of this panel, this trapezoid and this trapezoid. This is important. This, so this will be the total area. This is my Ly and this is my Lx. So Lx or Ly, this will be the total panel area minus this triangle and this triangle. We know the two triangle area which we already calculated. This is L square divided by 2, right? So this will give us the total area of these two trapezoid. So if we halve that area, so we will get the one trapezoid area, right? So as you can see here, this is my B3 and B3 is supporting two trapezoid area. So that why this one will be my equivalent area for this trapezoid. This is the mechanism, right? We will find out the area for any interior longer beam, right? Now what will be the equation? So area for B3 supported area, it will be Lx into Ly minus Lx square divided by 2. And now we need to multiply this with a factor, right? Why? Because this area, this trapezoidal area, load on the beam as shown, right, as we see here in figure, approximately convert it into an equivalent UDL. So we need to convert this trapezoidal loading, right, because this is a trapezoidal loading, right? This is, here we can see this is a trapezoidal loading. So that trapezoidal loading must be converted to a UDL loading. So if you convert this trapezoid to a UDL load, we need to multiply this area with a factor. We need to multiply this with a factor, right? And that factor equivalent UDL, right? And that factor will be F equals to 1 minus R square divided by 3 divided by 1 minus R divided by 2. So from this, right, where R is Lx divided by Ly, remember, right? We have to multiply this factor, but R will be equals to Lx divided by Ly. Now what will be the equivalent slab width? This is important, as in determined in case 1 and 2. So what will be the equivalent slab width? This is important. So the equivalent slab width for calculation of bending moment, will be the factor f, which we already calculated, multiply by the area, which we already calculated, square Lx divided by 2, that is the 2 trapezoid area, divided by Ly. Dividing by Ly means what? To convert them. So this is my trapezoidal area. So area must be multiplied with the factor and dividing that area divided by Ly. So right, so we need the load in units per running feet, right? Like we can say pound per feet, kilonewton per meter, kg per meter. So that's why we will need to divide the area by the length of the beam. So we know the factor, right? We know the factor. So the factor will be, it will be 2. So taking 2 as an LCM, we got here 2 Lx Ly minus Lx square divided by 2 Ly, right? Now next, taking Lx common, right? So taking Lx common, what we have, 2 Ly minus Lx, right? And here is my 2 Ly, and here is f, right? Now from here we just dividing this 2 Ly by this and by this one, right? So here Lx into, if we divide these two, we got here 1 minus, if we divide this one, so Lx divided by 2 Ly into f, right? And now what we have next, so next we have Lx into, we know Lx divided by Ly equals to r, so that why r divided by 2 into f, and f, so f is what? F, we know the value of f, the value of f equals to 1 minus r square divided by 3 and divided by 1 minus r divided by 2. If we plug this value right here, if we, let me write down here, right? So finally what we have here, I have Lx into 1 minus r divided by 2 into f. I just plug the value of r, that is r square divided by 3 and 1 minus r divided by 2. This is a factor. So here by just do the maths calculation right here, what we do, we can divide this with this one, and simply from this we can got Lx into 1 minus r square divided by 3, and this one will be the required equivalent width, right? This one will be the required equivalent width, which will be multiplied with the unit load Wu, and we will got pound per feet r kilonewton per meter, right? So this is the final width, right? And remember this width, we will use this width in our calculations. Now the next case is next beam is the exterior one, right? The exterior one, which is B4. So in the case of B4, right, we must understand this B4. This is the final case, 4 number. Now in this case, this is just only the half of that for the interior one, right? So this case, this is my B4. So the equivalent slab width, in this case will be the half of that one, right? So Lx into 1 minus r square divided by 3, it should be divided by 2, and you have to plus if we have any cantilever portion, if any, so we have to add that cantilever portion. So that why this is my the final equation, final width, right? This will give you the equivalent slab width for the case of before beam, and this would be further multiplied with the unit load to convert it into pound per feet or kilonewton per meter, right? So we will use this equivalent loading and equivalent UDL loading, right? Although this is not loading, it is just only the width. We have to multiply this with the calculated WU value, which is calculated as pound per square feet, or which is calculated as kilonewton per square meter. This is important. We will multiply that loading with this width and we will got the equivalent UDL loading. This is important, and we will do this type of calculation in our example. Thank you for watching. See you in next lecture.